Okay, this is sample problem 15.11. A mixture of 5.75 atmospheres of hydrogen, H2, and 5.75 atmospheres of I2, iodine, is contained in a 1 liter vessel at 430 degrees C. The equilibrium constant Kp for the reaction is 54.3. The equation is H2 gas plus I2 gas forms 2HI gas. Determine the equilibrium partial pressures of H2, I2, and HI. So this is a Kp problem. We solve it just like we would do a Kc problem, but we're just noting that this is the Kp value. Now note for this one, if you converted it to Kc, which is not a requirement, but remember Kp is Kc times RT to the delta N, where delta N is the number of moles of products that are in the gaseous form. So that'd be 2 minus the number of moles of gases in the reactants. So that's 1 plus 1, which is 2, which is 0. So that means delta N is 0. So that means RT to the delta N is RT to the 0, which is just 1, right? A number raised to the 0 is 1. So that means that Kp equals Kc. So you may notice that the value of Kp that we're using for this particular problem is the same value we were using in previous problems, even though it was Kc. And the reason for that is for this equation, the number of moles of gaseous products is the same as the number of moles of gaseous reactants. Just a little aside there. Now, as I said, you solve this just like you would a Kc problem. It's just your answers are not going to be in concentration units, molarity. They're going to be in pressure units, such as atmospheres. So, but you do it the same way, okay? So let's figure out what the initial concentrations are, and we'll calculate Q. Q would be the pressure of HI divided by the pressure of HI squared divided by the pressure of H2 divided by the pressure of I2. But if you look at this problem, there isn't any HI, so it's 0. Divided by the pressure of H2, which is 5.75. However, the pressure of I2 is the same, so we'll just square it, and that gives us 0. Q is less than K, right? Even though it's P, QP. QP is less than Kp, so that means the reaction goes toward the product side, so you're going to get plus 2x on the right side, and each of them you're going to get minus x on the left side. So let's put our initial in, 5.75, 5.75, 0. We've already figured out that because Q is less than K, we'll get minus x plus 2x. And then we just add those two terms to get the equilibrium concentrations, or pressures, in this case. Okay? Now we can go through the algebra. We know that Kp is 54.3. So I'm going to write out here that we have 54.3. Actually, why don't I just do it up here? 54.3 is Kp. And that is equal to the pressure of Hi squared, so that's 2x squared, divided by the pressure of H2, which is 5.75 minus x. However, I2 is the same, so instead of writing them out as two separate parentheses, just write squared. All right, can't do that if the numbers are different. If it was 5.75 minus x and then 5.15 minus x, you wouldn't be able to do that. But here you can. Okay. Now, when you have squared divided by squared, we said in a previous example, I think it was 15.8, that you can take the square root of both sides, right? And that simplifies it immensely. We now get 7.369 is equal to 2x over 5.75 minus x. We can now multiply the denominator by 7.369. So 7.369. Remember, don't forget to take the square root on this side. Times 5.75 minus x equals 2x. Distribute the 7.369 through the numbers in the parentheses, through both terms in the parentheses. Okay, so now you get, let's see, what is 7.369 times 5.75? Okay, so let me just write it out here. 7.369 times 5.75 minus 7.369x equals 2x. Okay, so I'm going to add 7.369 x to both sides so that the x is on the right side. Of course, that becomes 0, and that equals 9.369x. And it looks like that is 21. Actually, that's not right. What is 7.369 times 5.75? All right, I don't have it here. Let me just check that. 7.369 times 5.75. Looks like it's 42.37. So that's equal to, put it over here, 42.37 equals 9.369x. So now to find x, we divide both sides by 9.369. So 42.37 over 9.369, that would be equal to x. So 42.37 divided by 9.369, looks like about 4.523. So that's 4.523, okay? So there's our x, okay? Again, despite all that hard work, we've got to erase it here. I want you to leave that initial change in equilibrium table there. Okay, so now let's figure out what these are. The pressure of H2 is 5.75 minus x. So that's 5.75 minus 4.523. And it looks like that's about 1.23 atmospheres. Pressure of I2 should be the same, right? 5.75 minus x, so that's 5.75 minus 4.523, so that's 1.23 atmospheres. And then the pressure of HI is 2x, so 2 times 4.523, and that comes out to 9.05. Okay, so there's our final answers. Let's check to make sure they're correct. Remember, the last step in checking all of this is to use those equilibrium pressures, or concentrations if you're doing one with concentrations, plug them back into Q and see if Q is equal to K. We know K is 54.3. So pressure, by the way, let me show it this way. You don't have to put the parentheses in the expression for Q sub P. You know, for concentrations you need to use the brackets, but for pressures, putting parentheses is purely optional. I can just write it like this. I sort of like it like that myself. It doesn't look quite as busy. But if you feel like you want to put the parentheses around each term, you can do that as well. So that would be 9.05. Remember, it's unitless. Divided by hydrogen and pressure of hydrogen and the pressure of iodine, but they're the same. So 1.23 squared. And if you do that, I get 54.1. That's not exactly 54.3, but it's pretty close. So probably within rounding errors, we're okay. So that means that these are pretty good answers. At the end of this process, the pressure of HI would have gone from 0 all the way up to 9.05. The pressure of H2 and the pressure of I2 would have both gone down from 5.75 all the way to 1.23. So imagine it this way. I'm going to show you a little picture now that the calculation is done. And here's the idea. We started off with a bunch of H2s. The pressure of H2 was 5.75 atmospheres, right? So there's our H2. And then we also had I2s. And the amount of I2s was the same as the amount of H2s, 5.75. And the amount of HI initially was 0, right? We didn't have any. But by the time the reaction is over, here's what happened. The amount of H2 went down all the way to 1.23. It went down by about 75%. The amount of I2 also went down by about 75%. And the amount of HI went up from 0 all the way up to 9, right? 9.05 atmospheres. So it went up to even a larger amount than either the H2 or I2 originally in the problem. So there's a lot of HI at the end, right? That is the law of mass action at work. Essentially what happens is, physically, there is a constant called K, which describes what this ratio of HI to H2 and I2 is going to be. And that ratio is pretty high. It's 54.3. Right? So no matter what you put in as a mixture, with a couple of extreme exceptions, whatever the mixture you put in at the beginning, the end point will be a ratio that's equal to 54.3. So at the end, when it comes to equilibrium, you're going to have a lot more HI than you're going to have H2 and I2 because of that constant. So the reaction will move in a particular direction so that it comes to this value right here at 54.3. Okay? You know, just like something falling, right? Like if you have a ground here and you have stairs. Well, let's make these stairs a little bit bigger. Right? In the end, wherever you put the ball at the beginning, eventually it's going to fall down and end up down here. So it doesn't matter where you put it at the beginning, gravitationally it's lower energy down here. So it's going to end up at that point. And that's essentially what's driving this process here. It turns out it's energy. There's an energy of this reaction, or an energetics of this reaction, that leads to having a much higher pressure of HI than we have H2 or I2, even if the initial amounts of H2 and I2 are much larger than HI. Okay?